Please introduce Jacob Russell from Rice University, who will give us an introductory talk.
Okay. Thank you, Michelle. Right, so Genevieve asked me last week if I could sort of set some foundation and talk a little bit about hyperbolic spaces, their quasi-convex subsets, and this very nifty tool called the guessing geodesic lemma. And so I want to do those things, and I want to echo. Well, Genevieve didn't tell you questions. I'm going to tell you that you should welcome to ask questions. And if you, but also on top of that, like if at tea or at lunch you want to like come ask me more detail about things, I'm more than happy to talk about these. They're kind of my bread and butter favorite topics. Okay, so to frame these tools, though, I want to just sort of use this lemma of Kapovich and Rafi, and give it something to kind of work towards with these different definitions. Okay, so I'm going to sort of say the whole thing, and then we'll define each part of it, and then give a short proof. Okay, so this lemma says you start with a hyperbolic graph and a collection of quasi-convex subgraphs. You make this thing called electrification, and that is also hyperbolic with a constant determined by like the delta hyperbolicity constant and the C over there. Okay, so if those things don't make sense yet, it's fine. We're going to define them, but that's what we're building towards. This is a useful technique for constructing one hyperbolic space out of another. Kapovich and Rafi to show the free factor complex is hyperbolic for out of n. Okay, so let's define all these things that I didn't define. Red can be visible, Donnie. I'm going to use a lot of it. All right, so start with hyperbolic. Okay.
You draw very heavily with red, and you can face the consequences later when you erase.
That's right. All right. So a geodesic metric space is delta hyperbolic. Every geodesic triangle besides gamma 1, gamma 2, and gamma 3 has this beloved condition that I take any one side and it's contained in the delta neighborhood. Okay, so draw the obligatory picture. Take 3 points, join them by geodesics. And when the space is delta hyperbolic, these 3 geodesics are very thin. And so if I take a delta neighborhood of 2 sides, that covers the third. This is a delta neighborhood. Okay, so this is a sort of coarsification of the geometry of the hyperbolic n space. It includes trees and lots of other our favorite examples. I should underline delta hyperbolic. Okay, so these are the spaces that this lemma of Kapovich and Rafi are about. It's both you start with one, and at the end you get one as well. Okay. All right. Okay, so quasi-convex subset is the next thing. Oh, much lighting. Quasi-convex subgraph. Right, so this is any metric space. We're really going to talk about graphs, which are geodesic metric spaces, by making each edge length 1. Okay, but a subset Y of a hyperbolic space X is C quasi-convex if for any geodesic, called the gamma, based on Y. So that just means its endpoints are on Y. You have, well, I didn't. All right. Let's do it again. Yeah, that geodesic is contained in the C neighborhood of the subset. Okay, so if it was, let me draw a picture to illustrate. I have my space subset Y here. If it was genuinely convex, I would take any 2 points, then the geodesic between them would stay in that subset. It's not genuinely convex, it's quasi-convex. So when I draw the geodesic between those 2 points, it might leave the subset. It might even might leave and enter several times. But if you take a neighborhood, a C neighborhood of Y, that C neighborhood will contain any of these geodesics. Okay, so this is sort of loosening of the standard definition of convexity, and it in a very pervasive notion across geometric group theory. Like the theme of this conference is the geometry of subgroups, and the sort of first and best example of that study is the subgroups of a hyperbolic group, which are quasi-convex. Okay, let me give a couple of examples though. Things to think about. Okay, so the maybe sort of naive example is the definition of hyperbolic is basically this definition applied to two geodesics that share a single endpoint. It's a two geodesics with a shared endpoint. All right, if I take two of the sides of this triangle, right, that would be a quasi-convex subset in a hyperbolic space, because any geodesic that I pick will sort of go between the other sides, forming a thin triangle. Okay. This notion is meant to generalize convex subsets of H2, or Hn, I should say. That's another example. So you can think of like geodesics and polygons and horuballs. And then one that illustrates sort of the fact that you are in fact allowed to leave the subsets. Doesn't have to be actually convex. If you take the vertex set of a tree, so let me draw a picture of that. Because in many ways that's kind of this is sort of the example you should think about when you think of quasi-convex subsets. So I have a tree. My tree? Uh-oh. Oh no. Just look at the set of vertices. That's not a convex subset of the tree. If I travel between the set of vertices, but if I take the 1/2 neighborhood of any of the set of vertices, I'll contain any geodesic between any two. And if you want something that's maybe not almost the entire space, just take some sort of connected subgraph, take the vertices of that subgraph, and that'll also be a more of a sort of proper quasi-convex subset. Okay. Let me give you one more non-example as a contrast. I think the sort of canonical non-example are horospheres in Hn. Okay. So this is not want to say it. Let me draw. This is the upper half space model of H2. Let me use this orange one. I'll keep using red. Okay. So a horosphere is, I take any sort of horizontal line, and that horizontal line will define the horosphere through some value on the x-axis. Sorry, y-axis. There's a horosphere. Now, from our Euclidean eyes, that maybe looks convex, but in the hyperbolic plane, if I take 2 points, the geodesic between them will be the circle that's perpendicular to the boundary that goes through those 2 points. So it looks something like this. It's not a very good circle, but we'll pretend it's perpendicular. And so so that goes some distance from the red line, the red horizontal space. And if I move my vertices farther out, then the circle is going to, the radius of the circle is going to go up. And so I'll be farther and farther away from the space. So that's not a quasi-convex subset, because these geodesics sort of go arbitrarily far from it. All right, very good. Okay, so hyperbolic spaces, quasi-convex subsets. Electrification is a fancy word that Kasha doesn't know. Electrification. He was picking on me. Okay. But this is also often called the cone-off. It's maybe a term you've heard before. But it's a way of collapsing subsets of your space to have bounded diameter. All right. So I have script y is a collection of subsets of x. Okay, we're going to define the space that I'll call x hat is the electrification relative to this subset. Or sorry, it's this collection of subsets. Okay, so it's the space you're going to make by taking x, and for every subset in your collection, you want to crush it down so it has whatever its diameter is, and now it's diameter 1. The way you're going to do that is by joining every pair of points you're going to add an edge that connects every pair of points in your subset. So join every pair of points. Okay. Now if it's a random metric space, you need to join every pair of points. If it's a graph, you can just join like the vertices or vertices of y. Fine. And so if I do that, then now the diameter of the subset will be 1. Actually, let me keep this up. Okay, there's an alternative construction that's very similar, where instead of sort of adding a bunch of edges, you like between points, you add a single extra point to your space, and you join that one point to all the other points on the space. It's often called the cone-off. They're basically the same idea. Sometimes one is a little more convenient than the other. So Francois, I think, might talk about the other one in his talk, but we're gonna okay. So this is the space you're going to take your higher level space. You have a collection of quasi-convex things. you're going to collapse all of the quasi-convex subsets to a diameter 1 subspace, or like each one individually to a diameter 1 thing. Yes. I don't know. So I mean, like, okay, so Barb, that's what Barb called it. He like was you're short. Okay, you're short circuiting. Thank you, Don. You're making shortcuts, right? You're like, you're taking 2 points that are very, very far apart and adding them in. I don't know. Okay. Okay, so I'm gonna give an example before we. Oh, sorry. So yeah, so I'm gonna give an example. I'm gonna give an example of Calvin-Tropy's theorem before we discuss the proof. It's okay. I'm not gonna use a graph, but that's because the example is easier without a graph. But you could turn this into a graph example if you want. Okay, so the example of Calvin-Tropy. Okay. So the example I want to look at takes a genus 2 surface, or really any serves the hyperbolic metric, takes some curve, alpha, and we'll look at the universal cover of this, which looks like H2. H2. Okay. And we'll look at the lifts of all these curves alpha. So there's a bunch of geodesics in H2. Those are what's out. Okay. Okay, so the space here, X, is in Tropy's theorem, will be H2. If you don't like this being not a graph, you can think this should be pi1 of the surface and take its Cayley graph. But and the collection Y, well, okay, each of these complementary regions to the lift of alpha, like this section here. Each of those is a convex subset of H2, so it's a quasi-convex subset of this hyperbolic space. So the Y are the components of H2 minus the lifts of alpha. Okay, so then I'm going to electrify. So what does this electrification look like? Okay, so I'm going to kind of draw a schematic picture. So I take maybe this subset I colored in yellow over here. Add all this mess of edges, right? Every pair of points gets an edge. So that takes this whole region and turns into a bounded diameter subset, diameter 1 subset. Now, like, there are still points that are extremely close together in this region and in that region. Okay, so the bounded diameter subset from this one over here on the left of this geodesic is, distance sort of minimum distance 0 from this one. And so there's another region that touches up right against it like this. And by killing, by crushing both of these down to diameter 1, this whole geodesic also gets crushed down to diameter 1 plus epsilon. Does that make sense? These two sort of regions are kind of touching. Okay, but that picture happens everywhere there's a geodesic. So it happens there too. So I have sort of a couple regions like this, then it goes on, and it happens here. Okay. So I sort of keep drawing these little sets. Well, okay, so it looks very much like a tree. It's going to look like the dual tree to these curves. So if I put a vertex for each of these regions, and I join them by an edge, they differ by a lift of alpha, I get a tree. Okay, my picture looks finite valence, but it's actually an infinite valence tree. There's an infinite many lifts of alpha around each region. Okay, today maybe I won't use this board anymore. Okay, so this electrification, which is it's not quite a tree, right? Because there's all these diameter 1 sets are sort of very connected, there's lots of cycles, but it's quasi-symmetric to this dual tree. Okay, so this is QI, the tree, dual to lifts of alpha. Wait, I don't know why I spelled that alpha. That was very silly. Okay. Okay. So this is sort of an example of how Clausius' theorem works. You take your hyperbolic space, take a collection of quasi-convex things, you collapse them to bound diameter sets, and you get something new that's hyperbolic. Okay. Questions, comments, or complaints about that? Did I erase some boards? So the proof of this really goes down to this incredibly useful tool called the guessing geodesic lemma, which Donnie was insistent that I talk about. Donnie, you look puzzled. Okay. Okay. The guessing geodesic lemma. Okay, so this version is due to Bowditch, and it's sort of often attributed, the lemma is often attributed to Bowditch. But There are very similar theorems. Mazer-Minsky used one to prove the curve graph is hyperbolic. Hammond-Straw has a very nice one that's very useful, gives some very explicit constants. And the idea here is that instead of like, if you want to prove something is hyperbolic, you have to like grab these geodesic triangles and prove they're thin. But it can be kind of hard to understand the geodesics in your space, in an arbitrary space. So the idea here is that you don't have to actually prove the geodesic triangles are thin. It sort of suffices to sort of guess what the paths should, what the geodesics should be. Prove that for your guess of what the geodesics are, that those are thin. And then by some miracle, like those are basically the geodesics, and the space is in fact hyperbolic. That's very, but I don't think there's like a major theorem of hyperbolicity that doesn't use this idea. I could be wrong, but I don't believe there is one. Okay, so for this version, we'll have a connected graph gamma. Now, for each pair of vertices of this graph, B and W, we're going to assign a connected subset. Assign a connected subgraph P of VW, which contains these two vertices. Okay, so P, because you should think of this as like our preferred path from V to W. It doesn't have to actually be a path, it could be some bigger connected subset, but this is the thing I'm sort of guessing this should be the geodesic between these 2 points, or I'd like this to be the geodesic between these 2 points. Now I'm going to suppose there exists a constant delta, so that for all vertices, the GW U, we have 2 conditions. Okay, I'm gonna leave that there. I'll write the second half conditions over here. Okay, and so the first condition is going to be that these preferred paths that I picked out, they form thin triangles. And if that was, and the second condition is going to be a sort of, I don't know, it's often described as a coherence condition. It's going to make sure that I didn't distort distances like too much. So, okay, so the first condition, hopefully once I slide these up together, this will be a nice cohesive picture, is that if I take the path or the connected subset for V and W, that it's contained in this delta neighborhood of the connected subset for V and U and the connected subset for U and W. Okay, so this is the thin triangle property for hyperbolic spaces, but for these are chosen preferred paths. Okay, now if that was the only requirement, then this would say every single group is hyperbolic, and that's not true, so this can't be the only thing you need. So the second is that if you take 2 vertices that are joined by an edge, since one apart, then the diameter of this path you chose between them has to be bounded in your space. Okay, so now the magic is if you have these 2 properties, then gamma is delta prime hyperbolic for some delta prime that depends on this constant delta that satisfies these 2 properties. And not only is that true, these paths you guessed with are actually close to geodesics, and PVW is uniformly close to any geodesic between V and W. Uniformly close. Okay, so what that means is that I'm gonna draw a picture here. This path isn't actually geodesic on the nose. In fact, it can be very far. It can be sort of very inefficient if you sort of travel along that whole path. But it doesn't deviate very far physically from the geodesic. So if I have these 2 points, V and W, my preferred path might sort of be very meandering, have lots of backtracking, kind of be really inefficient. But if I look at just sort of as a set of points, and I look at the actual geodesic between V and W, they're going to be physically close together. There's going to be some neighborhood. The 2 sets are each contained in one neighborhood of the other. Okay. Any questions with the statements? It's really a powerful way of proving something's hyperbolic, because you don't have to actually understand the geodesics. You can sort of take your preferred choice of path. You can sort of wish what the geodesics are, and then voila, it's the right. Okay, so this is not so bad, but Alex Sisto has a really nice blog post on it, and I instead of regurgitating it, I encourage you to read it. It's like 12 paragraphs. It's very nice. Okay. So I want to use this to prove this theorem of Katovich and Rapi. Should we say this is, this is also the main tool that's used to prove the uniform hyperbolicity of the curve graph. I should say Bordich, like this delta prime, Bordich's result is, it's fairly explicit. I mean, he gives a formula for what it should be based on delta. Okay. Okay, so prove Katovich and Rapi. Is this result right here? Okay. Oh no. Okay, so in this case, I want to use the guessing geodesic lemma, and so gamma, my handed subgraph, is the electrification. The electrification of x relative to y. Okay. So to prove that gamma is hyperbolic using the guessing geodesics, I need to specify what my preferred path between two vertices are. Call vertices v and w. And well, I want to prove that this electrification is hyperbolic. I know x is hyperbolic, and so I'd really love if the paths in x between points were still the right paths in my electrification. That's not going to be the case, right? There might be a path that like runs through one of these sets that's y for a very long time. So when I electrify, like this like long geodesic will become diameter 1. But that's, that would be very nice if the paths in x were still sort of geodesics. Because that's going to be my guess that P of EW is just the x geodesic from V to W. And that assuredly will not be a geodesic in most cases, right? Because if I have, here's V, here's W. If that's the x geodesic, but there are 2 points on there that are both inside of some subset Y, or the same subset Y, then when I electrify it, those will get shrunk to have some distance of 1 between them. Okay, so the white path will not be a geodesic anymore because this distance is like, if they're traveling all this extra way, it's too efficient. I should have just skipped. Okay. But what's convenient is that this first property over here, that the triangle, these sort of paths, the path triangle within is automatic. So why is that? So distances in gamma are strictly less than distances in x. Right? Because what is gamma? It's the graph x, but I've added more edges, so it doesn't have to go down. And so if the fact that so thin geodesic triangles in x implies thin p triangles, right? If the two sides were gamma or delta close to 4, they're still delta close because distances have gone down. Do you want me to draw a picture? Does that kind of make sense? Okay. Then draw a picture. Okay. So, I mean, okay. So right, so I have these 3 points. I say, okay, I look in x and join them by straight lines, and I get the thin triangle condition, right? So two sides. I didn't draw very good. That's not okay. Now, when I add a bunch of edges, right? These neighborhoods, like from the point of view of x, they get larger, right? Because like maybe like this point way out here wasn't originally delta 4, but it's now it's closer. So in particular, like when I add edges, these two sides, their delta neighborhood in gamma still contains this set over here. Does that make sense? Now the problem is that these are no longer geodesics, right? That like there's probably 2 points on here that can be shortcutted around in an efficient way. But the thing, so does that make sense? And this is kind of the power. Is like I didn't have to do any work to get the thin triangle condition. I just sort of inherited it automatically. Okay, so now I need to check this second property. Okay, well, tried very long not to erase this. Now we're gonna play by. This is what we're proving. Take one last good look. Donnie was right. It's impossible to erase. Okay, so let's go to the second property. Okay, so I need to take 2 points that are joined by an edge in gamma. A little larger. V, W, edge. And I want to, now that edge is not P, right? Because P is the X geodesic, the X geodesic between them. And that edge might not be the X geodesic. Okay. So there's some other path that's connecting V and W, and I want to make sure that path is bound diameter. Okay, there's two cases. Because the edges in gamma come in two flavors. There are edges that come from X originally, and then these new electrification edges. So if I have an X edge between them, that's kind of the easy case. So in that case, P of VW is this edge. And so the diameter is 1. So maybe I was lucky and this is actually an edge in X, and voila. The harder case is I have an electrification edge. And so if V and W join my electrification edge, that means they were in the sum subset of my collection. Okay, so this means that V and W are inside of Y, or some Y. Some Y in my fancy collection. Okay, so let me draw the picture. So I have V and I have W, and they are inside of Y. There's some subset that contains them. Y. And P of VW is the geodesic in X between them. Okay, so this is like the picture before I electrified. This is P of VW. Well, this space is quasi-convex. So, sorry, the subset is quasi-convex. So there's some C neighborhood of Y that contains that geodesic. And this is the C neighborhood in X. Okay. But now the same kind of reasoning I had before. Well, when I add edges, distances go down. And so the C neighborhood from the point of view of X gets bigger, but it still contains that geodesic. Okay, so quasi-convexity tells us that P of VW is contained in the C neighborhood of gamma. And this is in, or sorry, C neighborhood of Y in gamma. Right? It's the C neighborhood of Y in X because of quasi-convexity, but X distances are larger. So it's also in the C neighborhood of Y in gamma. Okay. And so if I want to bound this diameter, I take 2 points. Those 2 points on my path between V and W, they are distance C from 2 points inside of Y. And in X, those points are very far apart, but in the electrification, they're distance 1. So I've added an edge of distance 1 between them. And so the diameter of this set P is going to be 2C plus 1. Okay, that's it. So these two facts together tell us, using guessing geodesics, that the electrification is in fact hyperbolic. And it tells us that the geodesics in the electrification are close to geodesics in the original space. Let me kind of draw a schematic picture of what that looks like. This is not going to be an accurate picture, but it's sort of how you should morally think about it. So the W, okay, so this is the X geodesic. This is what we were calling P of EW before. Okay, so oh wait, sorry, no, I'll take that back. That's a lie. That's not what I want to do. What I drew here, this is the gamma geodesic. This is not P of V. Yes, this is the efficient path between V and W in the electrification. And for each one of these edges, you're either in X or you're in the electrification. And so every time an electrification edge shows up, you can join these by this path PVW, by the actual geodesic in X. So there's some path that goes like this between these when it's an actual electrification edge. Okay. And so if I sort of do that for each one of these, okay, maybe this edge is actually an X, so I keep that one. And that red path I drew, that's the geodesic in X. And that, if I sort of think of how that parameterized map from the interval into the space, this is not a very efficient path, right? I'm spending a lot of time traveling distance 1. But if I just think of them as one of these sets, they're very close together, right? As I'm doing all that distance, traveling distance 1, I'm never going more than 2C plus 1 in the space. Okay, so the two sort of if I don't think about the speed at which you're traveling these paths, I just look at the image of these paths in space, they're close together, they're within 2C plus 1 of each other. So it's not so, you don't lose so much from sort of traveling along in X as you would traveling in the space. Okay, great. Questions, comments? Thoughts? Okay. Okay. So with that out of the way, this is the second half. I just want to sort of describe some properties of quasi-convex subsets, how you think about them. I imagine these will be used repeatedly throughout the week and next week, I hope. And the first set of properties I want to talk about are really about the projection properties of a quasi-convex subset. And there's a deep connection sort of in classical Euclidean geometry and even parabolic geometry between convexity and projections. And we see this carried over into sort of delta hyperbolicity and quasi-convexity. Okay, so just for a moment, think about that convex subset of R2. I can take any point in R2, and there's a well-defined closest point projection, where you draw the line that's orthogonal from your point to your line that's orthogonal to the line. That's a closest point projection. Well-defined, every point has a unique point on this line that minimizes the distance. And if I compare that to a non-convex set, like this V, and there are points in R2, like maybe if I pick up, if this V is perfectly symmetrical and I pick a point in the middle, well, there's going to be two closest points to that point, right? There's going to be one over here and one over here. Maybe that doesn't bother you so much. Maybe you're okay with having like bounded diameter sets, but this is problematic because if I move my point farther away, I should draw my a little longer. The projection gets bigger, right? The distance between my two projections gets larger. There's not really at least from the point of view of coarse geometry, a well-defined projection onto this non-convex subset. So in the world of hyperbolicity and quasi-convexity, we see a similar sort of phenomenon. So I'll have X will be a delta hyperbolic space. Y is C quasi-convex. And I'm going to define a projection from the space onto Y. So for all X in X, define, it's not enough room. Pi of Y of X to be the set of points in Y with the property that the distance between little x and little y is less than or equal to the minimum distance between x and capital Y plus 1. Okay, I always forget which way this inequality should go. So if y is in big Y, then covering that up and reversing the inequality, that's always true, right? Like the minimum distance from x to capital Y is bigger than the distance from a point Y. So the meaningful inequality is the other way. Now, if you cover that up and ask for equals, that would work if Y was closed. Y doesn't have to be closed. So you add this plus 1 to sort of guarantee that there's something not empty in this set. It's possible that if Y is not closed, there's sort of no point that realizes the minimum distance. Okay, but this is sort of more just the closest point projection onto this. And there's nothing special about 1. You could have picked 1/7 or something, some small number, doesn't matter. Okay, so this is more the closest point projection. But you have to be worried that, sort of by the way I define this is definitely not a single point, right? There's sort of many, so it's a set of points. But it turns out that it doesn't, let me start over here. It turns out that even though it's multiple points, the set of points that you have are bounded diameter. So I'm going to list a number of properties of this projection. I'm not going to prove any of them. And if you're curious, I'm happy to sort of walk you through / point you with the resources afterwards. So properties of pi of y. Okay, so there exists a number d, depends on delta and c. So that for all points, pairs of points, x, x prime, and x, you have the following. Okay, so the first property is going to get rid of this issue of what's the diameter of this set. This is what I call the Corsi-Lipschitz property. And so it says if I look at the projection of 2 points, and I take the diameter of those 2 points, have 2 points and project them, get some sets, take the diameter of their union. That diameter is bounded above by the distance between the 2 points originally plus this constant. Okay, so if I have my subset Y over here, I have my 2 points, X, maybe I'll draw them a little closer together. X prime. Okay, they project to some sets, and the total diameter of those sets is not much bigger than the original distance between the points. So this distance is about the same as that total diameter. In particular, when I pick the same point, X and X prime, then that distance is 0. And this says that these individual diameters are also bounded above by D. So sort of we maybe say it's coarsely well defined. Send a single point to a bounded diameter subset. Okay, and distances don't increase very much. I mean, like as a point of comparison to the classical case, right? The same is true. Like for this convex subset, it'll be a distance non-increasing map onto it. Okay. Second property, called a contracting property. And this tells us that not only the distances don't get bigger, but if you move away from your subset, they actually shrink rapidly. So if little r is larger than the distance from the point X to the subset Y, then the diameter of the projection Y of the R neighborhood of X, or the R ball around X. One more. That diameter is bounded by D. Okay, so let me draw a picture over here. I have subset Y. I have some large ball. It can be as big as I want as long as it doesn't touch Y. And it's
the R ball be disjoint from Y. So all less than this to Y.
Yes. Yes. Thank you. Yes. You're right. Thank you. Yes. I want the R ball to be disjoint from the subset. So I need this radius to be smaller than the distance to the. Okay, good. Thank you. That's right. I think maybe. Okay. Thank you. Okay, so I have this big ball. It's disjoint from my subset. It's centered at a point X. And this just tells me that like the projection is, sort of at most R plus D. Or maybe 2R plus D. But actually it's much better. This whole ball has this sort of contracting projection where it ends up as a bounded diameter subset. So the whole ball miraculously like shrinks down. You get this subset here, whose diameter is at most D. So you sort of think of this as like the space is running away from your subset really fast. As you move away from the subset, it sort of diverges very quickly from your subset. Okay. And the third property, which is secretly just this property in a different language, but it's a useful enough thing on its own to state. I'll give the name the bounded geodesic image property. So this says that if the diameter of the projection of my 2 points is sufficiently bigger than this constant D, then that implies that any geodesic in X from little x to X prime, any of those geodesics is going to pass close to both of these projections. So it'll intersect the D neighborhoods of both of these projections. Okay, so let me draw the schematic here. So again, put this one horizontally. There's Y. I have my 2 points, X prime, and I project them onto Y. And I notice that each of those gives me a bounded diameter subset, and they're very far apart from each other. If they're sort of sufficiently far apart, there's some threshold where they're that far apart, then any geodesic from X to X prime will have to sort of travel down nearby the projection of X, then travel over to the projection of X prime, and then go up. The statement tells you that you sort of only have to be nearby here at the projections, but you'll actually stay close to Y the entire time in between because of the quasi-convexity. This is maybe a good point to say, like, these different D's are different for, like, you give me a delta and you give me a C, there's a different number for each of these properties. You can pick the biggest one if you want to use the same one for everything. But this sort of, this D might be slightly different than that D. Okay, so this sort of tells you that, like, if there's a big projection, then the only way to travel, like, this sort of tells you like this subset Y is like in between X and X prime. Right? That when this projection is large, then the only way to go from X prime in the space is to sort of go visit Y in between. Okay. And maybe it's not, maybe you can convince yourself that these two properties are really sort of the same in different language. Okay. You mentioned which time? Okay. Okay. Let me mention. So one of my favorite little facts is that actually it turns out this projection properties they characterize being quasi-convex. So in a hyperbolic space, this is important because it's not true outside of hyperbolic space. Y is quasi-convex if and only if this is true about pi of y. So pi, like they always define pi of y for any subset of any space, but if that map or if that projection satisfies 1 and either 2 or 3. If you know that your projection is Course-Lipschitz and it satisfies this contracting property or this boundary property, then it has to be quasi-convex. So often you sort of prove, like this is very often you prove something is quasi-convex by sort of proving this contraction, this closed projection does what you want it to do. Okay, we have 5 minutes. Okay. So okay, I was going to define what a quasi-isometry was, but then I won't have time to say anything else. So if you don't know what a quasi-isometry was, I'm happy to spend the next 10 minutes at break explaining what a quasi-isometry is. So there's one more very important property of a quasi-convex subset, and this is why Gromov gave this definition in the first place, which is that they are invariant under quasi-isometries, and hence why we use quasi for both. So if I have a map between X and Z, that's a lambda epsilon quasi-isometry. And again, if you don't know what that means, please come bother me, and I'm happy to tell you afterwards. So I have this quasi-isometry, and I know X is hyperbolic. And that will imply that Z is also hyperbolic. Then a subset of X is C quasi-convex. Will imply that its image under F is C prime quasi-convex with C prime equal to lambda epsilon. Right, so this C prime is determined by the quasi-convexity of the original set plus the QI constants plus the delta hyperbolicity constant. Okay, so this sort of says that the specific constant of quasi-convexity is not preserved, but the being quasi-convex is. And what this means is that for geometric group theorists, it makes sense to talk about a quasi-convex subgroup, because any definition, any sort of geometric definition of a subgroup you give, if it's going to be a well-defined thing, it has to be invariant under changes of generating set. It needs to be invariant under quasi-isometries. So a subgroup H of a hyperbolic group G is quasi-convex if it is a quasi-convex subset of any finely generated Cayley graph. Okay, so G is you can pick some finite variance over G, get a Cayley graph. You look at a set of vertices in that Cayley graph that are in the subgroup H, and you ask, is that set quasi-convex? Okay. Now, thanks to this lemma, it doesn't matter which finite variance that you choose. If it's quasi-convex in one, it will be quasi-convex in all of them. And these are the sort of the first and best example of how the geometry of the subgroup is, or sorry, the geometry of the ambient group affects the subgroup. Oh, this is the next. Let me just finish with laying out some of the nice properties of quasi-convex subsets in hyperbolic space, hyperbolic groups. And like, in addition to being nice, it's also like extremely important. Like the whole virtual Hawking conjecture sort of rests on the nice properties of these quasi-convex subsets. Maybe not the whole thing, but a significant portion of it rests on these properties. Is that right, Donnie?
Yeah, everything rests on everything.
Okay. So if I take a hyperbolic group, a quasi-convex subgroup, Okay, so the first really nice thing that happens is that like this is a geometric property, right? It's just about how this set of vertices sits in the Cayley graph. But it has this nice algebraic consequence. H will automatically be finally generated. So automatically, I go from not knowing anything at all about H to knowing its finite generation. It has its own Cayley graph. It has its own word metric. And I can compare how the word metric on H looks to the word metric on G. Okay. And it turns out that the inclusion, H into G, is a QI embedding. So distances in H are only sort of distorted in G by a multiplicative and additive amount. Okay. Okay, well, what this means is that, well, G is hyperbolic. Hyperbolicity is preserved by quasi-isometries. So the only way for this to be true is if H itself is hyperbolic. And so all the wonderful things, hyperbolic groups are now automatically true for all their quasi-convex subgroups. Okay, I'll mention one more bonus fact that is not about H, but if you just take any element of G, its cyclic subgroup is quasi-convex. It gives you lots of examples of quasi-convex subgroups. Okay, I think that is all done. Thank you all very much.
What are examples of quasi-convex things where either like very close to convex things? Can you draw an example? Is there examples of stuff that aren't that way? Like a quasi-convex thing which includes finite house rotations.
Well, that's a good question. No, because you can take your set and you can add all the geodesics in every pair of points in it, and then you get. I mean, that might not, I guess that's not necessarily convex anymore, but like that's not necessarily convex on the nose. But sort of like those now you have a new quasi-convex subset where all the geodesics that you want are in there. I guess is there a good thing? So not in H2, the quasi-convex hole and the convex hole are the same. I don't have a good example. I don't think there really is a good example. But like, what does it mean to be convex in a Cayley graph? Like, I guess you could say the geodesics are between things, but that's kind of obfuscated. But like the point is like they're the same notion essentially. Sort of you need a little bit of fudge factor to handle all the quasi-isometries.